Alright, AP Physics 1, Unit 7, Lesson A, explaining the multiple choice here. So we'll start with number 2, ladders at rest, leaning against a wall at an angle. Which of the following forces must have the same magnitude as the frictional force exerted on the ladder by the floor? So let's put in a building here, or a wall. Let's see, this will work. So here's a wall, here's the ground, and here's a ladder. Now the ladder's going to be tricky, we have to rotate it, so we'll just do this. This is a side view of a ladder. Alright, rotator, put her over here. Okay. So, forces. So the weight of the object, the weight of the ladder is pulling straight down. Normal force by the ground has to be straight up. The bottom of the ladder, so this is normal force by the ground. This is the weight of the object. The bottom of the ladder wants to slide to the left. So friction, so it pushes the ground to the left. The ground must push it to the right. So this is our force of static friction by the ground on the ladder. All right, we need a force that's to the left then. Well, up here where it hits the wall, this wall is vertical, so it can only apply a force this way. This is the normal force by the wall. And that is our answer. It's going to equal out its leftward force, balances the rightward force of the friction. Uniform meter stick is balanced at its center, shown above. Which of the following shows how a 0.5 kilogram mass and a 1 kilogram mass could be hung on the meter stick so that the stick stays balanced? So the key here is, since we have twice the weight coming off of the 1 kilogram, it should be half the distance away from the axis of rotation, from the center. So putting them at the same distance isn't going to work. That's going to give the 1 kilogram too much torque. So I need whatever the distance is for the 1 kilogram, the half kilogram should be twice as far. So for example here, let's see, that's 1 unit, 2 units, and on the other side, for the half kilogram, it's 1 unit, 2 units, 3 units, 4 units. I like this arrangement right here, as a matter of fact. And what we're looking for is the smaller mass should have the larger lever arm by the same proportion that their masses are different. If one's twice as big as the other, then the lever arm should be twice as large for the smaller mass. Because remember, torque is lever arm times force. Alright? In this case, the forces are clearly perpendicular, so that's important, but that's why there's a little symbol like that. So a 1 kilogram is going to produce twice the mass, so it needs half of the lever arm in order to have the same torques for both of them. Horizontal uniform board of weight 125 newtons and length 4 meters is supported by vertical chains at each end. A person weighing 500 newtons is sitting on the board. The tension in the right chain is 250. How far from the left end of the board is the person sitting? Alright, so let's see. So I got this board, well here. So here's our board. And I got some forces on the board. I have its weight, which is acting right on the center. That's the 125 newtons. It's got 2 chains on it. That's not the guy. Like he was a rapper at one time, I think. And that's not the guy's name. I'm talking about the 2 chains on either end. Just saying. So when I say 2 chains here, well, you know what I mean. So chain number 1 is over here. Let's see. The right-hand chain has a tension of 250 newtons. So that tension's 250 newtons. We'll call that tension right. All right, and the person is sitting somewhere on here, but we don't know exactly where. We also don't know anything about the left chain. But here's what we can do. We're going to choose the left chain as our axis of rotation, since this thing's in equilibrium. And so right now, without the person on there, and we know this thing's in equilibrium, but right now I have my counterclockwise torques and my clockwise have to end up being equal to each other. Well, right now, which one's winning? If this is my axis of rotation, and this is my counterclockwise torque, it's certainly going to be bigger than my clockwise torque right here. The poor clockwise torque, it's got half the lever arm and half it's a fourth of the torque. So we need to put our dude somewhere on here. Anywhere he goes, he's going to help, but we got to figure out that distance. So I'm going to pick an arbitrary spot for him. In fact, I'll make him something I can move. So our person is going to be represented by this. There's our person. All right, so we'll put the person, say, here. And we need the torque by that person, which is also going to be, so this is the torque by person. If we look at it and we say, all right, all the torques that are clockwise have to equal all the torques that are counterclockwise. Well, the clockwise torques are the torque by the person plus the 125. You know what? Let's wait on putting numbers in. Let's not be too hasty. Torque by the weight of the board has to equal the torque by the right-hand chain, the tension in the right-hand chain. Now, they give us the length of the board or not? 4 meters. Okay. So I know the following numbers. I can put in the following numbers. And they are the weight of the person. I know that force. The person's 500 newtons. So I have lever arm, which I don't know for the person. So I'm going to call it L. Lever arm for the person times 500 newtons plus 2 meters, half of the board, times the weight of the board, 125 newtons, equals, let's see, the torque by the right-hand chain is going to be 4 meters away, and it's going to be 250 newtons. So I'm solving this for L. So I have 250 equals 1,000. Lever arm of the person times 500. So that's 750 equals lever arm of the person times 500. Divide by 500. I'm going to get that. So I got 750 divided by 500. I get 1.5, not surprisingly. So I got the lever arm for the person is 1.5 meters from the axis. Well, the axis that I chose was this left end. So this distance here to here is 1.5 meters. How far from the left end is it? Yep, that's what they want. So it's going to be big. Figure above shows a uniform beam of length L and mass M that hangs horizontally and is attached to a vertical wall. A block of mass M, all same mass I assume, is suspended from the bar at the far end of the beam by a cable. A support cable runs from the wall to the outer edge of the beam. Both cables are of negligible mass. The wall exerts a force Fw on the left end of the beam. For which of the following actions is the magnitude of the vertical component of Fw the smallest? Alright. So we want to minimize the vertical component of this. And it's attached to the wall, not just leaning against it, so it's got some sort of attachment, so that's why it can produce a vertical force here. Alright, so we want, keeping the support cable in the block as shown in the diagram is one option. Alright, but that means that this guy is supporting a lot of the weight of the bar, I believe. Moving the lower end of the support cable to the center of the beam and leaving the block at the outer edge of the beam. Let's keep going. Keeping the lower end of the support cable at the outer end of the beam and moving the block to the center of the beam. Moving both the support cable and the block to the center of the beam. I would say D. And I think it's easier for me to explain why I think D is right than to explain why the other ones aren't. See, we know the weight of the beam is acting here. If I move this so that it's also there, then this cable that's also there now will be responsible for supporting both of them because it'll be acting right through the center of mass of the system. And in that case, there will be no vertical component over here because it will be handling all of it because there's no torque on this because it's holding the center of everything. So I would go with D. Tough question, though, because there's a lot of them there that we could probably argue, trying to spend a lot of time figuring out which one's right and get yourself all confused. But that one is the best answer because the cord would hold everything and there would be no torque at all, so this wouldn't feel any force. An object weighing 120 newtons is set on a rigid beam of negligible mass at a distance 3 meters from a pivot as shown above. A vertical force is to be applied at the other end of the beam, a distance of 4 meters. Alright, so if the last question was difficult, this one should not be that difficult. The torque by the 120 thing should equal the torque by the force that you apply. And that means 3 meters times 120 newtons has to equal 4 meters times an unknown force. So I can divide right now by 4, and I would get 4 into 120 would be 30. So I would have 3 times 30, or 90 newtons. And so that would go with C. So if the last question was a little difficult, if you just tuned to this question, this one is relatively straightforward. This is a point waiting to happen for you on the AP exam. The previous one, that's going to be tricky. And what's really tricky about the previous one is the amount of time you might spend on it. So you want to be careful. 10. Massless rigid rod of length 3D is pivoted at about a fixed point W. And 2 forces, each of magnitude F, are applied vertically upward as shown above. A third vertical force of magnitude F may be applied either upward or downward at one of the labeled points. With the proper choice of direction at each point, the rod can be in equilibrium if the third force of magnitude F is applied at point. Alright, so where can we apply a force, either up or down? So right now, this is winning the battle. It's trying to rotate it counterclockwise, and this is trying to rotate it clockwise, but this is winning the battle because it has double the lever arm. So I need a force that's going to be applied somewhere. So W is right out, because any force I apply at W is going to not do anything in terms of torque. So I need to balance this one out. I could double the force over here, which would help balance out the fact that this one gets double the lever arm. So I could go, if I put it here, so I think V would work. If I do, because that would produce D would be the lever arm for this, and there'd be 2 forces. That would be the clockwise torques. The counterclockwise torques would be 2D times F. So they would be the same. So anything with V is in the running. All right, so here, here. All right, I'm going to rule out anything with W because that's not going to do anything in terms of torque. So that's gone. That's gone. Now, if you're a test taker and they put Y in there as a possibility, maybe, yeah, let's just say maybe that's a, but I can't put an upward force of F at Y. That would just really make that dominant. If I put it downward, these two would cancel. That's true, but this would then win because these two torques would cancel it out, but there'd still be this torque, and that wouldn't balance everything. So I don't see how Y would work at all. X I could do, X might work, but I'd have to pull it downward. And that would work because there would be a 1D, and this would be a 1D, and that would too. So I believe X, V and X is the correct answer. I don't think there's any way Y works. So I can rule out Y with a little bit of logic. That means V and X has to be the correct answer, without even being able to, needing to explain why X works. Although if you put it down here, this would be, these two would be 2, both of them would be DF. And that would equal to 2D times F, so they would work out the same. Figures below indicate forces acting on a rod in different situations. The lengths of the force vectors are proportional to the magnitudes of the forces. In which situation is the rod in both translational and rotational equilibrium? Alright, this thing, A, no way. Alright, if you pull this way and pull this way, that thing is going to rotate. And that is not rotational equilibrium. Translational would be fine, but the net torque would not be 0, even though the net force is 0. That's what it means to be in rotational equilibrium. The net torque is 0. Translational, the net force. C, the net force isn't 0 because they're both to the right. And if we assume this one is halfway through, the net torque still isn't. This would cause it to rotate then. So this one's definitely not either one. This one can't be, the net force isn't 0 because this force doesn't balance out that one. It's got to be B. If you think about it, this force is going to try to rotate it clockwise around its center of mass. This one's going to try to rotate it counterclockwise with the same torque because its distance from that center of mass will be the same. And they're translationally equal because the left and right forces are equal. So, the system consists of 2 spheres of mass m and 2m connected by a rod of negligible mass as shown above. The system is held at its center of mass with the rod horizontal and released from rest near the surface of the Earth at a time t equals 0. Which of the following best explains why the system does not rotate about its center of mass as it falls? Alright, for me, without looking at the possibilities here, the clearest explanation is that the force of gravity will act on the center of mass. This is a fact that we know. Well, anything that acts on the center of mass, which, by the way, for an object that's free to rotate in space like this, that will be the axis of rotation as well. So any force through the axis doesn't cause a rotation. So I'm looking for an answer like that. Let's see. The Earth exerts the same gravitational force on both spheres. No, it does not. It does cause them to accelerate at the same rate. So maybe my answer won't be one of the choices. But it's not because it applies the same force on each of them. The Earth exerts the same gravitational force on both spheres. No, it doesn't. No, it doesn't. Earth exerts a larger gravitational force on the sphere of mass 2m, but that sphere is closer to the center of mass, so the torques cancel out. That's the closest thing to a correct answer I've seen so far. The Earth exerts a larger gravitational force on 2m, but that sphere has more inertia, and so the torques cancel out. That sphere has more inertia, and therefore accelerates at the same rate as m, but that has nothing to do with the torques canceling out. I would say since 2m is closer to the axis of rotation, its torque is canceled out by this one's torque, so I guess C is the best answer. My answer is best, though. It's because gravity acts on the center of mass, and any force to the center of mass doesn't cause an object to rotate. As long as, it's free to rotate however it will. All right.